Welcome to Online Precalculus. This is section 2.2, Quadratic Functions. And our objective for this section is to recognize the characteristic of parabolas. We're going to graph all different types of parabolas, then determine a quadratic function's minimum and maximum value, and then we'll solve problems including quadratic functions min-max value, like word problems. So the graph of any quadratic function is going to be a parabola, okay? And that's this U-shaped or bowl-shaped graph, like the two you can see down below. And we know which way the graph is going to go, whether it is going to open up or open down based on the coefficient of x squared. So that's going to be this number right there, the a value. If it's positive, the parabola opens up like the one on the left, and it's negative, the parabola opens down like the one on the right. We have this turning point in the middle called the vertex, and that is always going to be the lowest or the highest point on the graph, depending on which way the parabola opens. So we have my vertex when it's opening up is going to be a minimum, and the vertex when it opens down is going to be a maximum. Okay. Also, a fun thing about the vertex is it happens to be the middle of the function. They are symmetric. So you can see, look at the word mirror here, okay? And you can see that this is also, it's not really straight, but this line or this word is symmetric. It has something called an axis of symmetry, right? That's just a line that cuts the shape, the picture, whatever. It cuts it in half, and both sides are mirror images of each other. Parabolas are always symmetric. They have an axis of symmetry. The two halves of the parabola will always match. Okay? So let's start graphing quadratic functions. In our earlier work with transformations, we used a series of transformations, right? Shifts, left, right, up, down, vertical stretch, vertical compressions, horizontal stretch, horizontal compressions, and reflections. We use all of those to help us graph different functions. So now we can use these same transformations to help us graph x squared, right? So the parent function, f of x is equal to x squared, is a parabola. The vertex is 0, 0. And it opens up or down if we start to put numbers in the front there. If a is positive, and we said this on the last page, if a is positive, the figure opens up. If a is negative, it opens down, okay? So those two pictures, right, these two pictures of the parabola also show the graph of a transformation, right? A function with a different vertex. So we move this vertex in both cases up and to the right, okay? We have a equation that we can use for a parabola that takes those transformations and incorporates them into the equation. And that is the graph of my parabola. You can see that we can still incorporate my shifts left and right for h, up and down for k. And if we are shifting every point in the parabola based on those numbers, we're also shifting the vertex. So instead of the vertex being 0, 0, like it is for the two black parabolas, you can see that the vertex is now h comma k. It's been shifted based on my transformations of right and up. This is called standard form of a quadratic function, or also vertex form. Okay. So either way, you want to call this. Some other text will put the one that we're going to do next as standard form, but we'll call this this one standard form and that one general form. Okay, but either way, whichever words you want to use for the name of this equation, the important thing is it shows you the different transformations. It shows me which way the vertex has gone. It shows me any stretch or compression or reflection. The parabola is also symmetric across the vertex. So with the line x is equal to h, that is the equation of the axis of symmetry. And we already said about up and down. Okay. So the sign of A determines whether parabola opens up or down. We said that. And if A is small, the parabola is going to be flat. And if the absolute value of A is large, it's going to be very skinny because it's going to stretch or compress vertically. So we need a procedure for graphing parabolas in this form, in standard form or vertex form. So the first thing we're going to do is we are going to figure out whether or not this parabola opens up or down. Okay, and we're going to tell that by looking at A. Next, we are going to figure out the vertex, and that's really the most important thing, right? You know, you can say, okay, it's nice to know whether it opens up or down because then I know which way I'm going to graph it and I won't make a mistake on that. But really, every parabola, when you start to graph it, you need to start with the vertex. And that's the method that I'm going to really go for graphing these parabolas, is we're going to focus on number 2. X-intercepts are nice, Y-intercepts are nice, but really, if we know the vertex, and we know which way the function is going to go, we can plot just the vertex and some additional points using transformations, using stretches and compressions to get my points. And I only have to graph half of a parabola because it's symmetric. I know it's symmetric. All parabolas are symmetric around the vertex, which means that if I graph the right half, I know the left half as well. So let's talk about this one. A is going to be -2 for this parabola. So that means it's going to open down. Okay. Next, the vertex. Well, looking at this equation, my vertex is going to be 3, 8. Okay. So I'm going to plot that. 3, 8, right there. Okay. So I know a few things. I know that that is the middle of my function. Now, yeah, you could plug in, you could set this equal to 0 to find the x-intercepts. You could plug in 0 to find the y-intercept, right? But I'm going to try to do this a little bit differently, okay? And what I'm going to do is I'm going to say, okay, the parent function behaved like this, right? Ooh, whoops, let's go with a better table. Okay, so the parent function behaved like this. At 0, plug in 0, you get 0. 1 gives me 1. 2 would give me 4, 2 squared. 3 squared is 9. And then I could keep going, right? 4, 16, 5, 25. I could keep making a table of values of my parent function. Okay, well, this is a vertical compression. So, or sorry, a vertical stretch. So basically, what's going to happen is the outputs of all these points, right? The y values of all these points are going to be multiplied by -2, okay? So instead of, well, we're still going to start at a vertex here. Next, instead of going right 1 and then up 1 from my vertex, I'm going to take this output and multiply by a. I'm going to take the output 4 and multiply by a. Take the output 9 and multiply by a, by -2. And then this is going to be, you know, off the graph at some point, okay? So we're not going to have to graph all of these points, okay? So here's my strategy now. is I could add 3 and add 8 to all of these points right there to get their true coordinates, or I could just start at the vertex, right? Start at this point and just count, right? That would be my vertex. That's my starting point. Okay, here's my next point. From the vertex, I went right 1, and now I'm going to have to go down 2. And this is from the vertex. So unlike graphing a line where you would just count from, the next point, we are going to always go back and start at the vertex. You're going to go right 2, 1, 2, and then down 1, 2, 3, 4, 5, 6, 7, 8. Okay, and get rid of these little dots. Okay. Then I'm going to go back to my vertex again and go right 3 and down 18. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, barely. And I could have done that a lot faster, right? Because this was 8, and then I'm going down 18, that's negative 10. Now, the good thing about graphing a parabola is you know that the vertex, this point, is the middle. That means every other one of these points is just reflected across that line. And now I have the graph of my parabola. Not perfect, but we have my graph of my parabola that I've made using, this is the transformation method. I didn't plot any points. I didn't do a lot of calculations. I didn't have to plug numbers into the equation, which you could, right? Instead of doing a table like this, we can make a table with my original equation, right? If I plugged in 0 here, that would be negative, right? It would be negative 2 times negative 3 squared plus 8. Well, negative 3 squared is positive 9 times 2 is 8, negative 18 plus 8, that's negative 10. Hey, look at that, negative 10. Okay, so instead of making a whole table with the values that I want to graph in my function, I was able to use the transformations and just count out the right points. Let's try again. Okay. So for this problem, again, I still need to know A. Okay, that tells me that the function is going down, and it's not stretched or compressed, it's just reflected. Okay, we need to know the vertex. Okay, with whatever method you choose to graph a parabola, the vertex is the most important point. So my vertex here is 1, 4. Okay, and that's really, again, all you need. 1, 4. Okay, my parent function, right? The points of my parent function. Let me be very clear with this. The points on my parent function would be 0, 0, 1, 1, 2, 4, 3, 9. These are always going to be the same. And then I'm going to change these. The inputs stay the same. The outputs get multiplied by a. 0 times negative 1 is still 0. That turns to negative 1. That turns to negative 4. This turns to negative 9. And then again, I could add 1 to all the x's, 4 to all the y's to get my actual coordinate, or just count. Write 2 down, 1, 2, 3, 4. Write 3 down, 4, 5, 6, 7, 8, 9. 16. Can we fit 16? No. No, we'll be one off the bottom down here. 16 will be like down here. Okay, but again, then we just reflect. It's symmetric. So we don't reflect across the x-axis or the y-axis. We take all these points and pull them across the axis of symmetry. And you get your parabola to look something like that. Okay. If this method is not for you, again, you can make a table, or we could follow some of these other steps back here to find the x-intercepts, to find the y-intercepts. Whatever way gets you a few of the different points is fine. Okay, but we do need more than we're going to need 3 or 4 points but you always need the vertex. You have to start with the vertex. And one of the big reasons why I don't necessarily want to always rely on plugging in numbers to find things like the x-intercepts is if we look at this equation, and the vertex here is -3, 1. So if I were to graph this, which opens up, it's not going to have an x-intercept. It's going to have a y-intercept, okay? But it's not going to have an x-intercept, okay? So this one is very simple because we're not multiplying by anything. So my parent function looks like this, right? I just have to count, right? So start at the vertex. Go right 1, up 1, right 2, up 1, 2, 3, 4, right 3, up 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? And again, if you had plugged in a number like 0, 0 plus 3 is 3, squared is 9, plus 1, 10. So your input would be 0, your output would be 10, and we have that point right there. Now reflect all these points across the axis of symmetry, and we get our graph. The axis of symmetry is, of course, always the vertex. One more of this type. Okay. Again, A is 1, so there's no stretch or compression. The vertex is 2, 1. So we have our vertex right there. I don't need to stretch or compress at all, so write 1, up 1, 2, 1, 2, 3, 4. 3 squared is 1, 2, 3, 4, 5, 6, 7, 8, 9. And I'm not gonna have room for any more. Reflect everything across the axis of symmetry and graph. And there's my parabola. Not a perfect drawing, but close enough. The next form that we're going to talk about is the form ax squared plus bx plus c. And unfortunately, if the vertex is h and k, there is no h and there is no k in this equation. So we can't just look at this equation and tell the vertex. Well, how do we find the vertex? Well, if we look at this algebraic manipulation here, we can sort of factor out an a from both of these terms, which gives me a fraction right there. I then can complete the square by adding and subtracting this term to the function, right? A times b squared over 4a squared, and then the same thing subtracted. Then when I complete the square, I have an equation that looks like this. Now, if you compare that to the vertex form, you can see that the h is represented by this number, and the k is represented by all that. Okay? Now, this is easier to remember than c minus b squared over 4a, two separate terms. Okay, so the important thing to remember is the x-coordinate of the vertex is going to be negative b over 2a. The y-coordinate of the vertex, instead of remembering this, which is a bit messy, just plug it in, right? If you plug in the x-coordinate, the y-coordinate is the output at that x-coordinate. Okay? So that means that the vertex of a parabola in general form here is negative b over 2a, comma, f of negative b over 2a. Okay? So you first find this and then substitute to get y. Okay? So we're going to have the same idea, the same procedure to graph the parabolas if they're in this form, if they're in this general form here. First, we're going to figure out if it opens up or down, depending on whether A is positive or negative. Then we're going to find the vertex. The vertex is always the most important part of graphing a parabola. So instead of just looking at the equation and saying, oh, it's H, it's K, we now are going to do these two calculations. Negative B over 2A, and then the function evaluated at negative B over 2A. I can still find the x-intercepts if I want. I'm probably really not going to do that. But the y-intercept is much easier because to find the y-intercept, you plug 0 in for x. If I plug 0 in for x in this equation, these two turn into 0 and we're left with just c. So f of 0 is always c, which makes finding the y-intercept if you're in this form very simple and a good way to check to make sure you're doing the transformations correctly. Okay. So let's take a look at this one. A is negative 1. That doesn't change. The number in front of x squared is still a. It still tells me my stretch or compression, which is not stretched or compressed in this case, but it is reflected, which means it opens down. Let's write that down. Opens down, just to make sure we know what we're doing here. Next, we need the vertex. Unfortunately, again, this is not something we can just look at and find. We're going to have to calculate it. The x-coordinate of the vertex equals negative b over 2a. So that would be negative 2 over 2 times negative 1. Okay, negative times negative is a positive. So we have a positive 2 over a negative 2, which is negative 1. Okay, so that's my x-coordinate of my vertex. I now need to get my y-coordinate. So the y-coordinate of the vertex, I'm going to plug in negative 1 into my function. And that's how you get any y-coordinate if you know the x-coordinate, right? Just plug x in, right? Use substitution. Exponents come before multiplication. So this turns into positive 1, so that's negative 1. Negative 2 times negative 1 is plus 2, plus 1, which would be a positive 2. So there's my vertex. My vertex is negative 1, comma 2. So negative 1, 2 right there. That is my y-intercept. Hey, look at that. Makes sense. No. There it is. Now it makes sense because my parabola is opening down. And it's going to follow the pattern of a parent function, right? It's going to follow this pattern from the vertex 1, 1, 2, 4, 3, 9. But instead of all these points, I'm going to multiply the y-coordinate by A, by the vertical stretch or compression. And in this case, it's a reflection. So we still have a vertex. That would be down 1 now. That would be down 4 and down 9. Okay, so write 1 down 1. I already got that. Write 2 down 1, 2, 3, 4. And always go back to the vertex. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9. 16 won't fit, which would be the next one. And again, I can just reflect all of these across the axis of symmetry in order to graph my parabola. Great. Let's try one more like that. Okay. And again, A is going to be negative 1. My vertex is going to be negative b over 2a, the x-coordinate, x, which would be negative 4 over 2 times negative 1, which would be a positive 2, which makes my y-coordinate negative 2 squared plus 4 times 2 plus 1, which would be negative 4 plus 8 plus 1. So that would be y is going to be 5. Okay, so my vertex is 2, 5. 2, 5. This opens down, right? Because the A is negative. So I'm going to just follow my pattern. Oh, and look, the y-intercept is 1. And that makes sense because I'm going to go right 2, down 1, 2, 3, 4. Hey, look at that. Very nice. From the vertex, right 3, down 9. That would be there. And I think now I actually have room for 5, 10, 15. Oh, look at that. I can squeeze in a 16. Okay. And reflect across. And there's my graph. The most important point for graphing a parabola is the vertex. And it also tells you the minimum or the maximum value of the quadratic function. And it's going to depend which way the parabola opens. Okay. So if we have a function, if a is greater than 0, the function has a minimum that occurs at the x-coordinate of the vertex, negative b over 2a. And that minimum value is the y-coordinate of the vertex, f of negative b over 2a. It's a minimum because the function opens up, right? Think of visualize it, minimum. If the function opens down, then you have a maximum, and it occurs at the x-coordinate of the vertex, and it is the y-coordinate of the vertex. So in each case, x gives you the location of the max or the min, and the actual max or min is the y, is the output, right? That's how high how high up or down the function goes, the y-coordinate. Okay? So without graphing, does this function have a minimum or a maximum? A is negative 3, which means it has a max because it opens down. Okay, so the second part is to find the min or the max, well, it's going to be a max, and determine where it occurs. In order to do that, I need to know the vertex. So it's not in vertex form, so I'm going to have to calculate negative b over 2a. So that's negative 6 over 2 times negative 3. So that's negative 6 over negative 6, which is 1. Plugging that in, 1 minus 13. So that's going to be negative 3 plus 6 minus 13, which is going to be negative 10. Okay, so my vertex is 1, negative 10. So the maximum value of this function is negative 10. It occurs at x is equal to 1. Okay? Find the function's domain and range. Haven't really talked about this in this section yet, but if you recall from the section with all the parent functions, the domain of a parabola is always all real numbers. And that makes sense because if we look at the function, there's no variables in the denominator to make a discontinuity. There's no radicals to give me something that's undefined. No matter what x you pick, you're going to get an answer. Okay. The range, however, because I know that this is a maximum, right? The range is going to reflect that. So it's going to go from negative infinity to negative 10, including negative 10, right? The range of this parabola, if we draw it, right, it keeps going down, but it does stop somewhere. So it goes from negative infinity to 10, negative 10. Okay, so same questions. Okay, and the first one is whether or not this has a min or a max. So a is equal to 4, which means it has a min, right? If a is positive, there's a min. The second part said find them. Okay, so in order to do that, I need the vertex. That's negative b over 2a. So that's negative 16 over 2 times 4. So that would be 16 over 8, which is 2. The y coordinate of the vertex would be 4 times 2 squared minus 16 times 2 plus 1,000. Don't get intimidated by big numbers like that. So that is 16 minus 32 plus 1,000. Seems kind of out of place though. Right, so that's going to be 984. So the vertex is 2 comma 984. Right? And the last is domain. Is again, all parabolas are going to be all real numbers. And the range, because this is a minimum, the range is going to go from 984 to infinity. Right? If you plug 2 into this function, you get 984. That's the smallest number you can get. The vertex. Okay? So there are many types of applications that involve finding mins and maxes of quadratic functions as well as where they occur. Let's try our first word problem here. So the question says, the picture shows that when a football is kicked, the nearest defensive player is 6 feet from the point of impact with the kicker's foot. The height of the punted football can be modeled with this quadratic equation, where x is the horizontal distance from the point of impact with the kicker's foot. So looks like it's going straight up, but if you think about the way a football works, you kick it up, it's eventually going to come back down, right? So we're going to get a graph that looks kind of like that. And I know I'm going to get a parabola because it's not a single x, it's an x squared. Okay, so the maximum height, where does it happen? It happens in a parabola at the vertex. So x is going to be negative b over 2a. So that's negative 1.18 over 2 times negative 0.01. Okay, so you are going to need a calculator for this, but if we calculate that, we get the negative and the negative cancel each other out, and we get about 59. Okay. Then, what is the maximum height of the punt and how far from, okay, so let's get the y coordinate of the vertex. The y coordinate of the vertex gives me, right, 59 squared plus 1.18 times the 59 plus 2. Plug that in my calculator, I get around 36.81. Okay, so that means that the maximum height is, and we're talking about feet here, so the maximum height is 36 feet or 37 feet, and it occurs 59 feet down the field, 59 feet away from the kicker. Okay, because that's the x coordinate, distance from impact, y coordinate, height of the punted football. Okay. How far must the defensive player who is 6 feet from the kicker's point of impact reach to block the punt? Well, here he is. He's got to get all the way up here. I can tell that that's going to be, maybe around, a little less than 9, 8 point something. But to find it exactly, why not just find f of 6, right? Because there's the function evaluated at 6, and that will tell me exactly how high he has to jump. Plus 1.18 times 6 plus 2. I'm going to put that in my calculator and get 8.72 feet. So possible, right? If he's around 6 feet tall or so, and he puts his hands way up in the air, and then he jumps, he could get there. Never know. If the ball is not blocked by the defensive player, how far down the field will it go? Okay, well, so now we're asking a different question. We're not asking for the vertex, we're asking for the spot that it lands. So that means that if we pull back up my graph here, right, we're asking, this is not going to be to scale, but we're asking, where does this go hit the ground? So we're asking for the intercept, the x-intercept. And the way you find that is with the quadratic formula. Okay, so we're going to plug this in. So we get negative b, so it's negative 1.18 plus or minus the square root of 1.18 squared minus 4 times a, which is negative 0.01, times c, which is 2, all over 2 times negative 0.01. Okay, so we're going to get two answers here. One of them, if we look at this graph, right, one of them is going to be back here. It's going to be negative. So we don't really want that answer, right? Because that doesn't really help us figure out how far it's going to go the other way. So if I do these two calculations, x is going to give me negative 1.7 and also 119.7, about, okay, rounding. So I don't want this answer, right? Because the football is not going to go backwards from the kicker. This is my answer right there. So if the ball is not blocked, it will go 119 feet down the field. Okay. And so to graph a function, all right, we're not going to make this perfect here, but to graph a function that represents this football's parabolic path, its y-intercept is 2, right? And then what's going to happen is it's going to go up and it's going to come back down. The vertex is going to be the point 59 and 36.81. And then this point is going to be 119.7. So also notice that 59 plus 59 is 118. So this point is not, right, the vertex isn't halfway in between. And that happens, it's still symmetric, but that happens because we didn't start at 0, right? So if we took a point right here, then that would be 118, right? Then 59 would be in between those 2 points, but not when we consider that we started a little bit higher, okay? So we can do this with any problem, any word problem that we have a parabola here. The two most important, there was this point that we cared about for 6, but in general, the most important points that are going to answer most of the questions about a quadratic function is the vertex and the intercepts. Okay? So we can use other types of quadratics to model verbal conditions. Once you make the quadratic function, you're probably going to have to find the vertex. So we can use the same sort of strategies to do that. Read the problem, decide if we have to maximize or minimize something, use the conditions of the problem to express the quantity as a function of one variable. That's important. We cannot solve an equation unless we can manipulate it into a function in one variable. We're going to put it in general form. We're going to find the vertex and answer the question. Let's see what I mean by this. Among all pairs of numbers whose difference is 10, find a pair whose product is as small as possible. Okay, so first we're finding the product of two numbers. Okay, there are plenty of, that's what we want to minimize. Decide what, right? That was my first sort of step here, is to decide what is to be maximized or minimized. Okay, because that's the quadratic that I want to make. So right now, the thing that I want to minimize is the product. So I'm going to multiply these two things together. Well, we have to express this product as one variable and probably is ultimately going to be a quadratic, but we have to express this as one variable. The difference of these two numbers is 10. So I can say that x minus y is 10. Okay, well that's good because if I subtract x from both sides, negative y is equal to negative x plus 10, which means y is equal to x minus 10. I now can substitute and change my equation from x times y to x times x minus 10, or x squared minus 10x. Now I have a quadratic. Now I have something that I can find. Okay, so if that's the product, if I want to minimize this, it's going to happen at the vertex. So that means the x-coordinate of the vertex is negative b over 2a. So that's negative 10 over 2 times 1. So that is going to be 5. Okay, and it also means that the y-coordinate of the vertex, well, I could plug it back. I have two equations, right? If I find x, I can just do y minus 10. I can also plug it back in here, right? That y is going to be 5 squared minus 10 times 5. So that's 25 minus 50. That didn't work. Let's plug it back into this equation. So 5 minus 10, and then y gives me negative 5. Okay? And so those are my two answers, 5 and negative 5. That would make my product negative 25, which is as small of a product as you can get. That would be the minimum. Okay? Let's do an area problem. So you have 100 yards of fencing to enclose a rectangular region. Find the dimensions of the rectangle to maximize the enclosed area. So here's your rectangular region, right? What's going to be minimized or maximized? The area. So the area is going to be, right, if we say this, x times y, length times width. So that's what we need to maximize. I have one more piece of information. I have 100 yards of fencing. So that means that the distance around this whole perimeter has to be 100, which means that 100 is going to equal 2x plus 2y. That's great, because now I can get y by itself and use substitution again. So that would be 100 minus 2x is equal to 2y, and divide out the 2 to give me that y is 50 minus x. Okay? So that means my area is x times 50 minus x, which is 50x minus x squared. Rewriting this in standard form. Okay. So what do we want to find now? We want to find the x-coordinate of the vertex, which would be negative b over 2a. That would be negative 50 over 2 times negative 1, which would be a positive 25. Okay, and then plugging right back into our simplest equation, y is going to be 25. Y is also going to be 25. So really, this enclosed area is going to be a square. And that was section 2.2, quadratic functions.